I apologize. The talk will be very similar to the one I gave at EPSM, but hopefully you enjoyed it then and you will enjoy it again. And so yeah, I'll be talking about flash or ultra-high dose radiation therapy. Martin asked yesterday, why is flash capitalized? We don't know why it is capitalized. It shouldn't be. Maybe we should just use not all capital letters, but just maybe the first one. Maybe we get some plan for the future. And maybe if there is a future for flash radiation therapy. So while preparing for this talk or any flash talk, and I tell you I have given many flash talks, I can basically go two ways. I can say flash is the best thing, tomorrow everybody should start treating patients with ultra-high dose radiation therapy. Or I can be saying flash seems to be a complete hoax. So I am probably leaning towards the hoax aspect of my talk here, but also please take into account the fact that I'm from Eastern Europe, so I do tend to be maybe a little more pessimistic at times, despite the name of my Xray lab. So take some of the information with a grain of salt, but I'll try to provide you with what has been happening in the field. And I'm not saying flash doesn't exist, but maybe it's overhyped a little bit. So let's get going then. So I do have some disclosures. I have Canadian funding to develop tools for flash radiation therapy. So I'm very interested in the research of flash radiation therapy. And I also have a consulting agreement with Xray Incorporated, and they are trying to develop an Xray flash system. So I will not be presenting anything on that project, but know that I have some. So conventional radiation therapy, you guys all should know about this. We know that it's typically delivered in fractions, a typical fractionation scheme, although we are moving somewhat away from that. It's about 2 gray per fraction. That's done to avoid normal tissue toxicity. It's typically delivered with 6 to 10 MB photon beams, but of course there's electron beam therapy and proton beam therapy. But since I'm showing here a very true beam linac, I'm just going to be talking about 6 to 10 MB photon beams. And we know that we need to shape the beams to the shape of the tumor and to modulate the intensities, and we do this by means of the multi-leaf colorimeter. I'm sure everybody here is very familiar with. Now, with the development of BMAT, for example, we sometimes, most often now, use a full rotation of the linear gantry to deliver radiation, and that's limited by some conventions. We cannot basically just have the gantry rotate, at 1 hertz frequency. So it typically takes 1 to 2 minutes to deliver a radiation fraction treatment fraction. So there's some limitations to how fast we can deliver radiation therapy. And of course, that plays an important role for flash radiation therapy or ultra-high dose radiation therapy. So we know that unfortunately, when we are delivering radiation, we would like to be killing tumor cells while not damaging any normal tissues. Unfortunately, that's not possible really at all. So we can look at these 2 sigmoid curves. You're probably familiar with those as NTCP and TCP. And if you look at, let's say, a certain radiation dose, see if you can see my mouse here, what we want to get is basically 0 adverse events and complete tumor control. Because these curves are reasonably close together, we can never get that. So if you are trying to get, say, 80% or 90% tumor control for the same dose, we get some adverse events. So we get some normal tissue complication. So what we are trying to do in not just radiation therapy, but in chemotherapy as well, is to widen the therapeutic window. So try to separate these 2 curves as much as we can so that we can decrease normal tissue toxicity while treating cancer. And again, this would apply for drugs as well, except there would not be radiation dose, but there would be treatment dose of drugs. Trying to widen it, and that's basically the goal of flash radiation therapy. So when flash radiation therapy came around about 2014, the first thoughts are like, oh, we widen the therapeutic window so much that we can treat cancer without any normal tissue toxicity. How wonderful would that be? You could do it in a single fraction. People just, patients just go to the hospital once, get their fraction. Cancer cells will be killed and normal cells will survive. That sounded very wonderful, didn't it? So what we are trying to do, we are trying to treat the tumor at ultra-high dose rates in a single fraction. At least that's what we were thinking in the past, and we moved away from this. And of course, this sounds great, but if you think about, a moving tumor, lung tumor, this comes with quite a few issues as well, right? We really have to make sure that we are hitting the tumor, because we are only treating, and now I'm just going to start saying some numbers, we are treating within, let's say, 200 milliseconds. So within 200 milliseconds, you can very accurately, temporarily miss the tumor, and that would be disastrous, right? So nobody really talks about imaging, but if you think about it, it's like, okay, now we have completely missed the tumor, now we hit it. So that's something that we need to be careful about. But again, imaging is something that people don't really necessarily take into account, at least at this stage, for flash radiation therapy. And I'm assuming everybody has heard about flash radiation therapy in the past, right? It's not completely new to you. Okay, so why are we talking about flash radiation therapy? So there was a paper published in 2014 in, I forget, Science Medicine or something like that, in which people, a French-Swiss group, was studying the effects of ultra-high dose rate delivery with electron beams on normal tissue toxicity as well as tumor control in mice. So let's just look at tumor control. So in this case, they were irradiating tumors, so head and neck models in mice, and these irradiations were done conventionally. I believe they used just an Xray tube, but also at ultra high dose rates. So their dose rates, or quoted dose rates, were about 40 gray per second. And they're looking at the tumor growth delay after, and let's look at these purple curves, which is 20 gray flash radiation, and blue curve, which is 19.5 gray conventional irradiations. And you see that for these two similar doses, the tumor growth delay for this particular case was the same. So they basically concluded, like, okay, the cell killing or tumor cell killing potential of flash or ultra high dose radiotherapy is the same as for conventional radiation therapy, which apparently is already surprising to radiobiologists, but let's not talk about that at this point. What they also looked at, and that was basically more important for their paper, was that normal tissue complications were reduced after flash radiation therapy. So what they did in one of their studies was to look at the probability or severity of radiation-induced lung fibrosis after thorax irradiations. And they looked at the radiation-induced lung fibrosis probability at 4 time points, but let's just look at 36 weeks post-irradiation, so you can see the last column. And again, let's look at the second column, which is 17 gray flash radiation, versus the last column, which is 17 gray conventional. And you can see that for the 17 gray flash radiations, only about 30% of mice exhibited some radiation-induced lung fibrosis, but for the 17 gray conventionally irradiated animals, basically all the animals had some radiation-induced lung fibrosis. So that was the one of the evidence that flash radiation reduces normal tissue toxicity. And if you're not convinced, although this is not extremely convincing either, but this is a photograph of a mouse that was irradiated to 20 gray with flash, and you see here the pigmentation, but no appellation or skin ulceration, which was apparently the case for conventionally irradiated animals. Unfortunately, there's no photograph to compare to, but that was not presented in the paper. And just note that I will talk about this paper a little later. So basically, this is a paper that sparked a lot of interest in flash radiation therapy and ultra high dose radiation therapy. I remember when I saw this paper for the first time, I was questioning the symmetry. Like, how do they know? Well, first of all, how do they know these were the doses that they delivered? And I think that this is not so difficult to measure. But also, I question, they used electron beams and they used high output Linux for flash radiation therapy, but much different energy X-ray beams for conventional radiation therapy. And they, of course, have very different properties in terms of attenuation. So that was maybe a little bit of a red flag for me, but then everybody was doing this research, so it was very exciting. At the same time, I knew there are many groups that were trying to replicate these results, and they were not successful maybe until 2019, until 5 years later. And I knew lots of people were trying, but were just not able to reproduce any of these results. Eventually, they did. Okay, so this was the very first paper. Then the same group continued doing research for ultra-high dose radiation therapy. They irradiated pig skin with 3 different doses, 28, 31, and 34 gray, conventionally, using just an Electron versus with flash with the same high output LINAC. And know that these LINACs were originally developed for non-destructive testing. Now we are trying to use them, or have actually used them, for treatment of patients, or single patient. And you can see that the conventionally irradiated skin shows necrosis. That's very obvious in this photograph on the left-hand side. But flash irradiated animals, there's some depigmentation, so you can actually see where the leaves impinged on the pig skin, but there is no necrosis. So in the same paper, they also published a study with 6 cat patients with squamous cell carcinoma that were treated to different doses of 25 to 41 Gray. And I thought it was kind of interesting that they showed basically a pretty wide range of doses. And this was again done with flash. And as you can see, 5 cats showed complete response at 16 months. But they just published this, in 2018. But just recently, the authors have started admitting that these cats actually developed necrotic tissues later on. So they were more late effects of flash radiation therapy that, of course, could not have been published in this paper because late effects didn't develop by the time they published this. All right, so then there was a patient study that was published, I think, for the first time in 2019, I believe, or 2020. And it was also kind of interesting because Jean Bobes, with the radiation oncologist, basically picked a patient, a 75-year-old patient with CD30 plus T-cell cutaneous lymphoma, who was treated many times for many lesions, I think over 100 times. And he picked 2 tumors that were treated with flash radiation therapy, one of them 3.5 centimeter in size with some bolus, and the other one was treated with conventional radiation therapy. And the very first paper that came out was actually just on the tumor treated with flash, but no comparison with conventional was presented in 2019, I believe. And it was not until this year when they actually presented the second lesion, or the outcome of the second lesion. And again, you can see that, this was a 5.6 MeV beam for flash with 0.5 centimeter bolus. The conventional one was delivered with 8 MeV electron beam from Electa with 1.2 centimeter bolus. But in this case, I think that's okay. But I would always would have liked to see for any of these flash studies if they're using the same beam except with a different dose rate. And that seems to be difficult to achieve because machines don't have the flexibility to run at such a different beam currents. But you can think about changing the duty cycle, for example, but that's not really done very often. Anyway, so again, this is a paper from this year. On the left-hand side, you can see the conventionally irradiated tumor. Seems like it responded well as the flash irradiated tumor that also responded well. So it seems like there's really no difference in response, which is good. But you can really not assess the normal tissue toxicity in this case either. It seems like there's not really much to go about. But the flash irradiated tumor responded well, which was good news. And again, this was done in Lausanne as well by Jean Bobes. Okay, so Jean Bobes now went on to run the first electron flash clinical trial. You might have heard about the Proton flash clinical trial. So this one is the electron one. And I believe the Proton one started before the electron one. This is just a phase 1. This is a phase 1 dose escalation trial for multi-resistant melanoma skin metastases. So it's this 3x3 dose escalation study. They're escalating the dose from 22 to 34 Gray, and they're basically looking at dose limiting toxicity. They are splitting the patients into different groups depending on the size of the tumor. And first patient was treated in June 2021. I haven't heard for a long time any updates about this trial, but maybe last year I heard that they moved on to the second dose. So I think the second one was 25 Gray. And that didn't show any toxicity. So this one is, as far as I know, still ongoing. So it's the first electron clinical trial for flash. And as I mentioned, most flash has been shown with electrons, and there's a good reason for that. Of course, I'm the crazy one who's trying to do photons. So the very first one, as I mentioned, is using this non-destructive testing LINAC. So it's the Unitron or Radiotherapy LINAC. And again, produces high output beams up to 500 Gray per second, or even I think kilograys per second if you deliver the radiation dose in a single pulse. And so depending on the beam, of course, the beam energy, you're getting only so much dose deposition at depth. At Stanford in 2018, I guess they started in 2017, they modified their clinical LINAC. It's a variant machine, I guess. in which they flip the gantry to 180 degrees, gutted it, basically put their sample as close to the source as possible, and they're able to get 74 Gray per second. And that's running it in the high dose total skin electron mode. Somebody talked about total skin today as well. So this is possible to do, and you get ultra high dose rate irradiations. Of course, the issue with this was a clinical machine, so they would run these experiments overnight, and in the morning they would treat patients. I would not want to be that patient. And at dark mode, it seems like their process was much less tricky. They modified also a variant LINAC. They are using now 10 MeV beams, and they basically, my understanding is that they are running it in the photon mode, so that provides much higher electron beam current, but not using the target. So it's basically the photons or the electrons are going unattenuated through the gantry, through the window, and they're able to get 240 Gray per second at the isocenter. You can imagine with the Stanford technique, another Stanford technique, your field size is much limited because you're very close to the source. When you are able to get ultra high dose rate at the isocenter, your beam sizes can be much higher, much larger, which means that you can irradiate larger objects with ultra high dose rates. And I think the beam size is maybe 10 centimeter or even higher or larger, which is quite nice. So those are just some modifications of existing LINACs, and perhaps you could modify one of your LINACs in the clinic here as well. I think it does come with some issues, and I've heard one story in which a hospital modified their own LINACs, and because they're using such ultra high and such high dose rates, their MLCs basically faulted. Electronics wasn't happy, and they had to make sure that it's again functional for treatments in the next morning. So there can be some unpredictable issues with modifying a LINAC that's not meant to run at ultra high dose rates. So something to keep in mind if this is an area of research that you are planning to be involved in, which I think you should. Okay, so why not electrons? Why electrons and not photons? The reason is in physics, which is nice. So if you think about how photon beams are being generated in your LINACs here, you have an electron beam that's interacting with a high atomic number target. These machines, it's tungsten. And by Bremsstrahl interactions of the electrons with nuclei of the tungsten, you're getting X-rays. And those are the X-rays that can penetrate deep in tissue, which is, of course, what we want for deep-seated tumors. Unfortunately, this process is not very efficient, and that's the reason why everybody's using electrons and not photons, because photons are difficult to produce at ultra-high dose rates. We look at how does the interaction of the electrons with photons look like. We know that electrons don't, unfortunately, only interact through Bremsstrahl, they actually interact through collisions with the electrons of the atoms. And basically, some of the energy of the electrons is converted into radiation, and that's what we want, but some of it is converted into heat. And that's what we don't want, because at some point the target actually could melt. So for a 10 MeV electron beam, turns out that radiated and collisional stopping powers are pretty much equal. So 50% of your energy of the electron dose now is going into heat, and only 50% is going into photon dose. Now, even though these photons or X-rays are forward directed, not all of them go in the area of your interest, so you lose some efficiency of the electron to photon dose conversion right there. And if you also look at how much radiation, how much dose does a photon deliver compared to an electron, it's actually a factor of 20 lower for photons compared to electrons. So all in all together, we get about 1 to 5% efficiency of converting the electron dose to photon dose. And of course, you could say, oh, let's just ramp up the beam current if you can on your LINAC and irradiate with 100 times more electrons into the target. What could happen is that you would just be depositing too much energy into the target, generating too much heat, and the target would melt. And all of a sudden, you're thinking you're irradiating the patient with 10 MeV photons, but it's actually 10 MeV electrons at the dose rate that's 100 times higher, and of course that would be disastrous. So we do not want that, and we have to be very careful. Okay, so this is since this is so challenging, we thought, well, why don't we look into this? And we basically in 2018 proposed that we could modify the TRIUMPH aerial electron LINAC. So it's an electron LINAC at the TRIUMPH laboratory, which is in Vancouver, close to Victoria, where I live. and they are creating or generating high-intensity electron beams. And of course, that's just the precursor to generating a high-intensity photon beam, because now we have to actually build a target. And that was not extremely easy, but we tried to do that. So we basically took one of the concrete boxes and converted it into a flash radiation station with X-rays, or tried to at least. So this is the model. This is the beamline going inside the shielded box. So it's not just concrete, it's a lot of lead. There's a lot of lead lifting done during this project by two students, Luca Egerizzi and my PhD student, Nolan Esplin. And this is the design of the target. In medical physics, we like tungsten is the target. In high energy physics, they like tantalum a little better. So they're very similar materials in many ways. So we basically designed a 1 millimeter tantalum target that was explosion bonded on aluminum flange that was actively pulled with water. We were trying to do everything we could to make sure that the target doesn't melt under the stresses of the electron beam hitting high intensity electron beam. So we, of course, had to run lots of Monte Carlo simulations to figure out what the electron beam will do with the target and how many X-rays it will produce and at what dose rate. But we also had to run thermomechanical simulations to make sure that the heat that's deposited in the targets, and transferred to the aluminum flange is not detrimental to the experiment, that the target will not melt. So we've done that and ran some simulations and realized that the dose rate that we expected should be about 200 gray per second, which is great, right? It's way above the 40 gray per second magical thresholds that we think is the one that elicits the flash effect. So it was exciting, but of course, this is just simulations. And when putting this in real life was a little more challenging, but we eventually did it after many years of going back and forth with people at Triumph and always finding a new group of physicists who were not happy with what we were doing. So there was a lot of iterations, but this is the actual tantalum target that was put on the beamline. And again, in the hope that we would be getting ultra high dose rate 10 MV photons. We eventually put everything together, ran some film measurements, some scintillator measurements to actually look at the temporal profile of the beam. We 3D printed a mouse in a different project for dosimetry, so we used that for some dosimetry experiments as well. And the goal was to irradiate lungs of healthy mice and look at radiation-induced lung fibrosis. So if you pay attention, this will be, if you were at DPSM, that's not your first photon beam flash that you will have seen. But there's the flickering screen is actually the delivery of the flash beam at, I think, 150 milliseconds. So we did manage to irradiate some mice. We have run into lots of issues, so maybe I should just stick to physics experiments and don't do any biology experiments because they're a little more challenging than physics experiments. But this is an example of the 15 gray irradiated animal. Of course, on the left-hand side, it's the control animal. Flash irradiated animal is in the middle. And you see no lung fibrosis, but you do see some fluid in the conventionally irradiated mouse in the left lung. That was this micro CT image was taken at 8 weeks post radiation, and the fluid cleared 12 weeks post radiation. So we definitely saw some effects of radiation. I also have to say that this is not an easy effort. It's not like running mouse experiments in the clinic when you take the mouse, anesthetize the mouse, put it in the beam, walk out of the room, hit the button, go retrieve the animal. Seconds later, or a minute later, every animal here takes 1 hour to irradiate because it's a huge hall with all these high energy physics experiments and beamlines, and just to ramp up the beam and set it up with the parameters that we want takes about half an hour. It also takes about half an hour to cool it down, and somebody has to walk in the room, make sure that nobody's in there. In the physics department, you have one last man out button. There is like 7, and you walk a pretty fine path, which is not half a kilometer, but it's probably a couple of 100 meters. So anyway, it was quite challenging. We had to have 5 people to run the beamline. They tried with 3 at some point. It was a complete failure. Okay, so just so you appreciate that this is actually a very, very challenging experiment. It was still very interesting and quite nerve-wracking as well because we had to have so many people on board for this. So we irradiated the lungs with 15 and 30 gray. We're still analyzing the data for 30 gray. We also noted that we had basically no imaging. The only thing we had there was a camera, so our targeting wasn't the best. So if we continue with these experiments, we have to make sure that we actually can image the animal. and make sure that we are irradiating the lungs and not the guts, because the guts are much more radio sensitive, we learned. Anyway, so it was kind of exciting. Unfortunately, we did want to be the first ones in the world to irradiate animals with ultra-high dose rate X-rays, high-energy X-rays. We were not. A group in China, in Chengdu, from the superconductor in Linac, the Perther facility, actually developed a different system, although similar to ours, but much smarter, in which they were using a rotating target. So now the heat can be dissipated over a much larger area, and they were able to achieve dose rates up to 1,000 Gray per second, but only 6 to 8 MeV. We are using 10 MeV, so maybe a little better there in a way, I suppose. And they were taking measurements with fast current transformers, with scintillators, with films as well. They built a Monte Carlo model, so they built some, a very, very nice beamline for irradiations, but similar to ours. You can see that the animal is actually placed very close to the target, which means that if you are trying to irradiate patients, this is still not going to happen with X-rays or ultra-high dose rate X-rays. They've also performed some animal experiments, so these are just survival curves for 30 Gray flash and conventionally irradiated thorax, and on the top, and for abdominal irradiations for 12 Gray for biopsy mice, which is what we used in our experiments as well. And they saw a very clear difference in survival between flash and conventionally irradiated animals. And the good thing about this study was also that they did actually use the same beamline. They just lowered the beam current or increased or decreased the duty cycle. So this is something that I always want to see. Okay, so this is something I did not present at EPSM. So we, at the University of Victoria, while running these experiments at Triumph, we figured out, well, actually, maybe you can get these ultra-high dose rates with a very, plain vanilla X-ray tube that we have even in my lab. And so we basically, the trick here is to make sure that the X-ray beam is not filtered at all. So you're basically just using the beam that's filtered by the beryllium window, and you have to place your sample as close to the focal spot of the X-ray tube as possible. So we have done that. On the left-hand side, you see some actually film measurements, but we first ran Monte Carlo simulations of a number of X-ray tubes that have the shortest distance from the focal spots to the outside of the X-ray tube, and we found out that yes, you can indeed get up to 140 Gray per second with a really cheap X-ray tube. The issue with that is now that, of course, these beams are not filtered, so they're very low energy and they attenuate in depth, very quickly. So you could maybe get dose rates of 40 Gray per second at only 2 millimeters in depth, but that might be sufficient for some experiments. And again, this is something that's really easy to get. And on the right hand side, we have some experimental validation, so at 2 different depths from the film measurements that are shown on the left. And there's a really good agreement from what we expected based on Monte Carlo simulations, which is quite not given, because if you look at, again, the spectrum, we are basically simulating 10 to 11 kV X-rays. So those are really low energies, and typically these cross sections are not as well validated as 6 MV beams and so on. So that was quite nice to see that we got a good agreement. The issue with our beam is that it's a basically therapy X-ray tube with a stationary anode. So to turn the beam on takes about a second. To turn the beam off also takes about a second. And if you're trying to do an irradiation that takes 200 milliseconds, it's just not going to work. And you're going to have beam on for 2 seconds at least. So we had to build a shutter system, and we basically sort of immersed the shutter system inside the X-ray tube. And if I have a better drawing, I don't necessarily. So this is the shutter. It was just a slit that was basically rotating inside the X-ray tube window. And on the right-hand side is the Monte Carlo model of the shutter slit. Now, this was our first idea. It worked okay, but we didn't realize that we're going to have a huge dose non-uniformity, which we corrected by designing a different shutter. And I'm not going to be talking about. We did validate the system with some film measurements, but also with scintillator measurements. So we have really small, this one's actually bigger, but we have some 5 millimeter 0.5 millimeter scintillators in diameter and length. And we were able to measure the profiles shown on the top as of the beam, basically, for irradiation times as short as 10 milliseconds up to 100 milliseconds. We're also able to measure the doses for a 25 milliamp current with the different scintillators as a function of exposure time. And we saw a very beautiful linearity. So basically, we could either increase or decrease the beam current or increase and decrease the exposure time on the shutter system. And we are getting a really nice agreement with what we expected in terms of dose. The doses that we are getting are about 200 Gray per second, but in a small, shallow sample. Now, if you're trying to irradiate something really small, there's not too many small, biologically small things, or small things that are useful for biological experiments. But it turns out that the larvae of Drosophila, of fruit flies, are actually pretty small. They're about 5 millimeters long, which is fine for our system, or even less. And then they're about maybe 1 millimeter in thickness. So we thought, well, maybe we can see, we can irradiate Drosophila and look at maybe survival after total body irradiations, because targeting these will be probably a little more challenging, but not impossible. We have talked about that as well. So my student Alex Hart has been running these experiments, and you can see it. So basically, we have this small holder that we put double-sided tape on. We stick the larvae on top of the double-sided tape, put it into our irradiation system, and set the irradiation time depending on what we want in terms of doses. Then we put them back into their tubes that are filled with mashed potato powder. That's what Drosophila larvae alike. And then we are looking at basically the emergence probability or rate. So this is some of the first experiments that Alex has run, and you see that for the different doses delivered with ultra-high dose rate or flash radiation shown in red, and conventional radiation therapy, basically we saw much higher survival for ultra-high dose rate compared to conventional. So it was very promising. Alex was really excited until we bumped up the numbers from 10 larvae to about 60, and the difference is not as clear by any means. So it was kind of interesting. When you run small numbers experiment, it could look really good. I guess it could look the other way around. But with now 60 animals, the difference it's still there, but it's much smaller than what we see over here. And I unfortunately don't have the newest data. Anyway, so we talked about electrons. We talked about photons a little bit. There's more photons, but we'll talk about those. So how about protons? Yes, protons in pencil beam geometry can also deliver ultra-high dose rates, just by definition of how these proton beams are being generated. And Eric Defender from UPenn actually ran a mouse experiment in which he used doubly scattered proton beams, and you see sort of the dose distribution superimposed on these animals, and irradiated the guts of mice, and looked at normal tissue toxicity, but also looked at tumor control. And these are the results. So they irradiated tumors to 12 and 18 Gray, and you see that in green flash radiation versus conventional irradiation in red, the tumor growth was delayed the same way, pretty much. Maybe a little less with flash radiation, but it looks like there's some overlap. But again, what was interesting for their study is that flash protons induced less intestinal muscle thickening, which was an indicator for of fibrosis post-irradiation, which is shown in the plot on the left-hand side. And muscle thickness was increased after conventional radiation therapy in red compared to flash radiation therapy. And again, that's basically points at reduced normal tissue toxicity. And of course, Varian was very interested in these results, even though the beamline that was used for this experiment was not a Varian beamline, it was an IDA proton beamline. And Varian founded this flash forward consortium that originally was supposed to sort of enhance or provide collaboration for people using proton beams for flash radiation therapy and bring flash radiation therapy into the clinic. Eventually, they opened up their consortium to people that are using other particles as well. But it was a big thing, flash forward consortium to bring flash radiation therapy into the clinic. Now, proton flash clinical trial was started in 2020, I believe, or 2021, and it just recently finished. And this was the first ever clinical trial for flash radiation therapy. It was basically just to assess the feasibility and safety of flash radiation therapy. So they chose a study for 10 patients. They delivered 8 Gray in a single fraction and ultra-high dose rate to painful bone metastases of the extremities. I think the maximum number of lesions was actually 2 lesions per patient, and they used 200 MeV transmission beam. So they did not take advantage of the bragg peak at all because of maybe the symmetry issues, and basically just shot the beam through the patient as is shown on the top right side. The trial was called FAST-01, and just at Astro about a month ago, the results of the trial were announced. So this is just the cohort of patients, again, 10 patients, 5 male, 5 female. These are some photographs of the treatments, and basically they were looking at the frequency of adverse effects, such as edema, erythema, extremity pain, fatigue, and so on. And basically the conclusion of the study was that these adverse effects were not any different compared to conventional radiation therapy after flash radiation therapy. So it was very promising, and again, the result was that the ultra-high dose rate proton flash therapy is feasible in clinical settings. So that was important, although maybe not very exciting, but important. And as a result, they just announced in June, I believe, even before these results came out, the FAST-01 trial, which will be a very similar study that will be treatments of bone metastases in the chest. And if you're following physics world, I really like talking about flash because I can always say this just happened yesterday or this just happened last week. So just last week, 6 days ago, this proton flash clinical trial was announced as the top 10 breakthrough of 2022 by physics world. And that's all physics, right? It's not just medical physics. So that's kind of exciting. But I'll get back to that later as well. Okay, so what was the first in human proton flash irradiation? Actually, it turns out that it happened a very long time ago. In 1978, on July 13th, Anatoly Bugorsky was running some experiments in Protvino in Russia. And it seemed like that the beamline, the U-76 accelerator, was not really working properly. And he decided he was going to go take a look at it. Stuck his head, in between the beamline. It turned out that it was working somewhat, and basically received a very high dose rate and dose of 76 GeV, proton beam. This is how he looked like after irradiation. Apparently, the edema was even worse as the time progressed. And you can see that the beam basically entered through the back of his skull and exited through the nose. It's estimated that his head received about 2 kilogray, the back of his head received about 2 kilogray, and the nose received about 3 kilogray of dose. Of course, it was a pencil beam, so it was good. And apparently, in 1978, everything was super secret in Russia. Probably nothing changed since then. So he couldn't really talk about it. But he was brought to a hospital in Moscow. Protvino is about 100 kilometers north of Moscow. And basically, doctors were watching him, observing him, and they were expecting him to die within, a couple of weeks. But that didn't happen. He actually, there was some edema, you see some skin depilation as well. But he actually did quite well. And basically, apart from the fact that his nerves and his left side of his face were completely destroyed, and his skin basically didn't age or hasn't really aged since. He's still alive. He was not very much affected by this very high dose irradiation. So it was kind of interesting. Apparently, he had a couple of seizures throughout his lifetime, but still finished his PhD. So first flash irradiated patients. And reportedly, he said he didn't feel any pain, but he saw a flash brighter than 1,000 suns. So maybe that's where the flash name comes from. But it's very interesting. Okay, so talked about electrons already, but I'm really a big proponent and very interested in very high energy electrons, PHEE. I don't know if you have heard about them, but you will at this point. So we know that when we use electron beams in the clinic, they only have such a certain range beyond which we cannot use them for treatments. And for example, for an 18 MeV beam, we are expecting the range to be about 9 centimeters. If you're trying to treat something deeper, you will not be able to do so with 18 MeV electrons. Well, it turns out that if you bump the energy of the electrons up to, in this case, for example, to 100 MeV, you actually get a very different depth dose curve. And that seems to be quite promising for treatments of deep-seated tumors. And it turns out that that actually is indeed the case. And when I was at Stanford, I was actually working on a project to investigate those distributions delivered by very high energy electron beams. And at that point, it was maybe 2012, we had no idea about flash radiation therapy, but it turns out that you can get ultra high dose rates with very high energy electrons, and that might be capable of delivery of ultra high dose rate radiation therapy. So this is a design of the phaser machine that Belu came up with, and it's supposed to have a compact high gradient electron liner that should be able to accelerate electrons to 100 MeV in 1 meter. So that's very different from what we have in the clinic. And you could have electromagnetics scanning and steering all the way towards the patient, and then you can have a steerable high energy electron beam, basically like pencil beam scanning that you have with proton beams. Electrons are actually in a way, much easier to work with because they're much lighter than protons, right, about 2,000 times lighter. So the bending radii of electron beams are much smaller than bending radii of proton beams. So your facility now, the hope is that a linac like this would fit into an existing linac hole, as opposed to protons, as you know, you need an entire facility. So we developed in collaboration with Race Station Research in Monte Carlo, basically treatment planning system that used pencil beam scanning optimization, similar to what you see over here. And this is for a video. So here are some of the results of the basically treatment planning study. On the top, we have the dose distribution with very high energy electrons. In the middle, VMAT, and that's the dose distribution of the plan that the patient was actually treated with. And at the bottom, you have differences of very high energy electrons minus VMAT. And basically, whatever is blue is less dose to normal tissues from very high energy electrons. So it was kind of exciting. You can look at DVHs, and basically all the doses to organs at risk were lower than dose in very high energy electron beam compared to the VMAT beam. So that was kind of exciting. I was very excited, but apparently radiation oncologists did not get excited even by 30% differences. It wasn't good enough. Anyway, but what was interesting at the time, and even more so now, is that the treatment time to deliver the entire dose was estimated to be about 1 second. And that's taken some properties of a random very high energy electron beam line. There's not too many random ones. There's probably only one in the world at this point. But if you can think of increasing the beam current, you can possibly achieve these ultra high dose rates. And again, this is something that we have done before flash radiation therapy was even announced. So for me, it's super exciting to see that CERN is actually collaborating with the Lausanne University Hospital. Those are the people who first observed the flash effect to build a new cancer radiation therapy system that would actually take advantage of very high energy electrons. So you can see the design here. It seems like we'll have basically just 2 beams, which is kind of interesting, but probably a little more feasible from an engineering point of view. But the goal is to deliver very high energy electron radiation therapy. And I think this was just mentioned in National Geographic 2 days ago or so. So maybe I should have put it up as well. So it's it's a lot of fun, I think, and I'm happy that my students actually spent 3 weeks at CERN last month and ran some very high energy electron experiments. So hopefully that was fun for them. All right, so now I'll move on a little bit to dosimetry, because dosimetry of ultra high dose rate radiotherapy is not necessarily straightforward. If you think about ionization chamber and you're blasted with a lot of X-rays, electrons, doesn't really matter. You'll get a lot of ion electron recombinations. That's not what we want, right? So if you look at the ion collection efficiency as a function of dose rates, dose per pulse, you see that up to maybe 0.1 Gray per pulse, the collection efficiency is almost 100%. But if you go to dose per pulse of about 10 Gray, and this is something that we are thinking about flash in terms of flash radiation therapy, your dose, your ion collection efficiency decreases significantly to less than 30%. So you think, okay, maybe if we know what it is, it's not such a big deal, but then eventually it becomes these ionization chamber and ultra high dose rate beams become unreliable. And we have to come up with some, either other ionization chambers or other devices that will be capable of reliably measuring dose rates. Again, this is important that we deliver the appropriate doses to the patients. So this is from a study by, again, Monte Carlo from the Swiss group, in which they were looking for dosimeters, alanine, TLD films, and ionization chambers. And we're delivering 10 gray and looked at the response of the different dosimeters as a function of dose rate. So the bottom right, we have 0.1 gray per second, the lowest dose rate. And on the top left, we have the entire 10 gray dose delivered in a single pulse. Single pulse in their system lasts about 2 microseconds. So they're basically delivering mega gray per second, right? So extremely high dose rates. And you see that all the dosimeters seem to be performing reasonably well. Some of them has been error bars of 10%. Maybe that's not what we want. But the issues with most of them is that we really cannot use films, TLDs, or alanine for beam control, right? You cannot wait 24 hours to realize, oh, we have irradiated a little too much. So we definitely need some active dosimeters. And people are working on ionization chambers, basically making them smaller, because in smaller volume ionization chamber, the chances for ion recombinations are just smaller because the ions don't have to travel such a large distance. But this was, reasonably promising result, I would say. But this is an active area of research, and people are looking at new dosimeters, and I think I'll them a little bit. Now, possible explanations of flash. We really don't know what causes flash. How come tumors are responding, the same way to flash as the conventional, but normal tissues don't respond the same way? So the very first idea was basically oxygen depletion during radiation therapy. So oxygen is responsible for radiation damage as well. We know that hypoxic tissues are radio resistant, so we need to up the dose. And basically the idea behind this was that when we are irradiating with ultra high dose rate, oxygen is depleted and there is not as much damage done to tissues as it would have been with conventional radiation therapy, in which oxygen is being replenished. Now there's an issue, like why would this work on normal tissues and not on tumor tissues? And the reasoning behind that was that tumor tissues are already hypoxic. So the difference in the hypoxia level is not as important in tumors as it is in normal tissues. So basically those are interesting to see the progressions, like, oh, it's definitely oxygen depletion. Second paper, yeah, probably not, because it would be tricky for the oxygenation levels that we see in normal tissues. And the third paper says it's absolutely not oxygen depletion. So, and I don't think, again, we are quite set on this, and depends on whom you talk, they will tell you a different opinion. And the other one, which I think is interesting, is that the flash effect might arise from immune cell sparing. And the idea behind that is that basically in our bloodstream, we have a number of circulating immune cells. And if the irradiation takes a long time, more than 60 seconds, apparently that's the circulating time of your blood, the entire blood volume. If the irradiation takes 60 seconds, so all of the circulating tumor cells will be irradiated because it takes so long. It doesn't matter in what part of your body you're going to be irradiating the immune cells that will not be able to repair normal tissues. Now, if your irradiation is very short, you'll be able to spare some of the immune cells that will help with the repair of normal tissues. Now, Professor Jin is contemplating also, depends on where you are irradiating in your body. If it's the heart, you're going to be irradiating most of the volume. And also depends, I guess, how far from the heart you're irradiating, as well as what your dose rate is and what your target is. So it's an interesting hypothesis, but I'm not quite sure that has been proven as the correct one either. I'm not a radiobiologist, but I think it's a very interesting issue to look into. So there have been many, many radiation therapy studies looking at different sites with different particles, and this is just a list. I counted maybe 20 studies or so that have demonstrated the flash effect. So, maybe we should just go and treat patients in the clinic. Sorry, maybe not, because all flash RT might not be rainbow and unicorns. And you might know, it's not that easy to publish negative studies, but thankfully some people have been able to do that. So actually one of them is from Australia, from the Australian Synchrotron, in which they have looked at the partial body and total body irradiations after ultra high dose rates, and they basically found no difference in toxicity after flash versus conventionally irradiated animals. There was another study done by MD Anderson, in which they basically saw that there was no normal tissue sparing in cardiac and splenic models of lymphopenia and gastrointestinal syndrome, which was also an interesting study. And then the third one was on proton flash radiation therapy in zebrafish embryos. and they looked at a very large number of scenarios, and let's say 10 of them, but only one of them show some flash effect. So thankfully, people are publishing some of the negative studies. And I just took the liberty of quoting some of my colleagues about flash radiation therapy. One of them says, flash is interesting. It doesn't quite do what we want it to. Some things show differences, others don't. It's very confusing and difficult to make it tell a consistent story. Another one says, my beef with flash is that many groups have seen negative data, but they aren't publishing it. But maybe they're trying, just not going through the review process. And the last one is from a radiation oncologist, and who says, flash delivery sounds scary. I will certainly not be an early adopter of this technique. But more often I see it like, yeah, we want to treat patients with flash, which to me sounds scary. All right, so now I'll go into an issue about scientific integrity. If you don't know Elizabeth Bick and you're on Twitter, okay, should not be promoting Twitter, I suppose. But Elizabeth Bick is, I believe, a neuroscientist who is interested in scientific integrity. So she developed a software that basically can go through your paper and say, oh, this data is manipulated because it's copied, from one side to the other. I don't think we can often see it in physics. Well, I'll show you that unfortunately we can see this in physics. But for example, from biology, when people are showing slides, often it's the same slide, just slightly shifted or rotated or mirrored. And her software can identify these issues, and then she contacts the journals, and the authors are not in a good position in that case. It can happen by mistake, but it actually can be done intentionally. So she actually just, maybe last month, published an article in the New York Times, and it was entitled Science is a Nasty Photoshopping Problem. And I'll show you some examples of that. Unfortunately, there's a reason why I'm bringing it up in this talk. So this is one of the figures from the first Proton paper from 2014, in which they are showing basically the progression of cancer by bioluminescence imaging. They are looking at sham irradiated animals, control group, in other words, 15 Gray conventionally irradiated and 28 Gray flash irradiated animals. There's lots of, BLI images. I can see how things can get mixed up, but can they get mixed up this much? Whatever is shown in a red square or in the same color square, it's just duplicates. So, not great, but I suppose this can happen because you are indeed dealing with a lot of images. Another figure in the same paper, they are showing that basically there is more radiation damage after 15 Gray conventional irradiations compared to 30 Gray conventional irradiations. And so those are, again, bioluminescence imaging data. And if you look at the control group and the 30 Gray flash irradiated group, it actually turns out that it appears to be the same mouse, except the color map is slightly different. So perhaps use a different window and level. I myself actually am not completely convinced about this data that is the same. I have looked at it, too much. And again, this is done all with software. But if this is the case, and I think the authors actually did comment on this, that this was actually done by mistake as well. But this is a big deal, right? If you're trying to show that flash is the same as control, that's a big no-no. But still, possibly this could happen. What could not happen is in this figure, when you're looking at basically the radiation dose is measured by CSN2, no idea what that actually is as for dosimeter, but methylviologen is shown on the top right. And again, it's a dosimeter that shows basically how much radiation was delivered. And you can see the methylviologen data. Of course, this never occurred to me. I've seen this plot so many times. Why would you put the legend over your plot, over your data, right? You're always taught not to do that. Well, maybe there was a reason for these people. They took the segment that they measured for 15 microseconds, copied it 3 times, and in one of those copies, they flipped it around. And this clearly is manipulation of data. Is this the only dosimetry system? It's not the only dosimetry system, but it is definitely questionable and makes you, question the integrity of this entire paper. But this is all published on PubPeer. You can actually read the conversation between Elizabeth Bick and the senior author, Marie-Catherine Bozanin, about this paper, but the responses are not, very satisfying, I would say. So now you can imagine that this is something that actually is, flash radiation therapy is not a thing, but so much money and resources have been put into flash radiation therapy. Again, we have results from other people showing that they saw the flash effect. So maybe it's not as concerning as one could think, but we have to be careful about what we publish. There was a lot of money dedicated to flash research. This is just data. This is just number of citations. Proton et al. And you see, as I said, like in the first few years, there are not too many citations, but now lots of people are, presenting positive data, which is great. There was a lot of money from the National Institute of Health that has been dedicated to flash research over the last 4 years. Not even 4 years. It was about $23.6 million that was dedicated to flash research. Hopefully it is a thing, but maybe it's not as beautiful and as powerful as we thought it was at the beginning. However, it's not all so bad, right? If we are able to treat patients in less than 1 second, why not do it if we can develop the tools for it? So for example, if we have to develop novel ultra-high dose rate dosimeters. They should be dose rate independent, provide online readout with high temporal resolution. And there have been a few groups that have been looking at novel beam dosimeters, such as this beam current transformer, which is just measuring the induced current by the beam that's passing through. It doesn't interact with the system. There's a Cherenkov dosimeter. Really, it's not absolute dosimeter, but it can tell you how much dose relatively you're delivering in each pulse, and the time resolution of the Cherenkov dosimeter, which is read out by a photomultiplier tube, is 2 nanoseconds. So you can actually measure every single pulse, which is very interesting. It was actually quite interesting to see that from a very young LINAC, is that the first 6 to 8 pulses actually deliver very different doses than we think they do. Which of course is not a problem when you're delivering thousands of pulses for treatment, but you're delivering 1 or 2. Now you are seriously underdosing the patient. Apparently, this was reproducible. They've done many measurements, but this is something that we need to know. But we can only know about these numbers when we have a dosimeter that can provide ultra high frame rates output. This is some study from our groups when we are looking at lead-doped plastic scintillators that don't have such a high temporal resolution, but they are very, very nice dosimeters as well. So people have been looking at new dosimeters, and people are looking at new systems now. So the Intra-Op now are developed basically their Magdalena system now can deliver ultra-high dose rates. So some institutions are purchasing this, and they're actually treating. I think the second Electron clinical trial will be run with this Intra-Op system. There's PMB-Alsen, which is the manufacturer of the original non-destructive testing LINACs. They developed a new electron beam source, as well as Radiotherapy in California, and is now looking at developing ultra-high dose rate machines. So, even though there's a lot of money dedicated to flash that, had some manipulated data in the first paper, there are still really good outcomes of this entire research. Okay, so I'm just go very briefly through the last few slides. So protons possibly could be the future of flash radiation therapy. Mevion is another proton beam proton therapy manufacturer, and they are now offering this single room system that fits into your LINAC. And Billy Lou here is saying that future of proton therapy is coming, and he's hopeful that we can deliver flash radiation therapy with protons, with this Mevion system, which of course will be wonderful. And remember, the first clinical trial, which was the breakthrough of 2022, was delivered with a proton beam. But unfortunately, on November 9th, the Siemens Healthineers CEO, Bernd Montag, announced that Varian will not be actively marketing or pursuing new sales of proton systems anymore. So Varian, who ran the first clinical trial, is now basically backing out from flash radiation therapy and from flash proton radiation therapy because they are no longer supporting protons or new proton machines. So that is kind of interesting and makes you wonder about the future of proton flash. Again, we don't know what's going to happen to the Flash for a consortium, but they could still focus on electron beams, which is something that Varian has not really been doing so far. Okay. The flash effect was indeed demonstrated for electron, proton, and photon beams. So there's definitely data that supports that the flash effect exists. That was done in multiple anatomical sites, and it seems to be a very promising treatment modality. but I don't think we'll be treating, every single patient with flash radiation therapy, at least not anytime soon. We have more flash questions than answers, but as long as it works, it's fine. And many groups are investigated ultra-high dose rate of flash radiation therapy. And I think we need everybody to do ultra-high dose rate research to make sure and to understand, what patients could possibly benefit from this. I'd like to acknowledge my collaborators, sources of funding, and I would like to thank you for your attention. Happy to take any questions, but this is Vancouver Island, almost as nice beaches as in Perth. Questions? No questions?
There's a question from Marco in the chat.
Yep.
Do any flash studies show worse toxicity outcomes?
Yep.
Or do all studies show better or equivalent toxicity?
Yeah, so there was this study from Smythe et al. From your synchrotron from Anstock, right? They say it right. And he's actually showing for one of the partial body irradiations. I'm not sure if it was the brain, the thorax, or the abdomen, in which they have actually shown worse outcomes for flash radiation therapy compared to conventional radiation therapy. But for that study, it was kind of not clear what the dose rates actually were, and there might have been a lot of discussion about that. But in their studies, yes, they are showing worse outcomes, worse toxicity for flash. But nobody else has, as far as I know.
Let's get another question. So there have been other things that have been shown to improve therapeutic ratio, like hypothermia,
Yep.
or use of gold nanoparticles, which are seemingly technically achievable compared to flash. Why is there so much excitement about flash?
I think it's, as far as I'm concerned, because it was sort of overhyped. Then, the authors claim that, we can do single fraction. There is very little toxicity, even though the symmetry wasn't really clear. Yeah, I think that's because, it showed such great promise based on the statements of the, original authors. I think it's also seems like a little bit of a paradigm shift, right? Now you have to come up with the new machines, you have to come up with new dosimetry, so lots of room for research as well. So that's maybe those are the things that I can think of made it so exciting.
A lot of the studies were showing flash with high dose rates in single fractions. Is there much research in multiple fractions?
Yes.
Reducing the treatment time?
Yes, yeah, there is at least one study. I think it was for total brain irradiations. And they did look at a number of different fractionation schemes. I think they started with single fractions, and I think maybe 4 fractions was the largest one. But the question is now, what is the dose for your larger or higher number of fractions treatments? And basically, they have shown that maybe 4 fractions was just too many, and the flash effect was not conserved. But it seemed like for 3 fraction, I forget exactly what the doses were for single versus multiple fractions, but for 3 fractions for that particular scenario, the flash effect was conserved.
Yeah.
So but yeah, not too many people have done that.
Is there much discussion on like a risk-benefit analysis of having such a high dose rate and dose in a single fraction if you were just to miss your target a little bit? Maybe that's why there's a lot of hesitation from oncologists.
Yeah, I wish there was more hesitation from oncologists. But yeah, that's something that I don't think actually people have looked into, or at least I'm not aware of these studies. But yeah, it's definitely something for me. Like if people are thinking about proton therapy that has already an uncertainty in the range, and now thinking about this uncertainty in temporal, I guess delivery or the temporal aspects of the delivery, combining protons with bragg peak and flash seems completely outrageous to me. And that's probably one of the reasons why people are using, shoot through beams, transmission beams for protons, because they don't have to worry at least about this uncertainty. But this is actually a really good idea, I think, for a paper.
Yeah, it's hard.
Quite highly cited.
Yeah, it's kind of difficult because if you're treating like 1,000 times more patients than you could, like every 1,000 patients you like really mistreating it and actually causing a death or something like that. Yep. And also at the same time, if you're having deaths because of bottlenecking in a department, you're not getting enough treatment. So it's like kind of
So to be fair, I think even though the treatment time is much shorter, we know that lots of the time is spent on the couch setting up.
Yeah.
So I don't think it's going to be more comfortable for the patient when they don't have to watch a gantry go around for a couple of minutes. But I think the throughput would be increased, but not,
Right, yeah.
by a
Still
factor
have
of,
all your setup, all this kind of thing.
That's right. But that's actually a really good idea.
Yeah, I'm not sure whether I misunderstood.
Yeah.
You mentioned about are there some centers that are treating that?
There
You mentioned
are a number of
trials.
clinical trials, yes. So
Are
one
they
trial.
using electrons? Or
Right, so one of them is using electron beams, and I think they're thinking about another one, so it's the impulse trial. I think it actually might already be using the Magdalena machine, and that's basically just on the skin, right? Because it's easy, you can see it doesn't move. So yes, they're using the Magdalena to deliver treatments to melanoma patients. And the other one was with protons, which was metastases of the extremities thing. But that one is done. They're just thinking about starting a new trial. But nobody's treating without a trial. This is all clinical trials. Nobody's treating patients with flash on a routine basis. That's not possible at this point. And I think both these clinical trials have to go through a number of exemptions, and they have to make sure that this is allowed by their governments, both FDA and in Switzerland.
Okay, we'll bring it to an end there. Thank you very much for that, Magdalena, and for your visit to Perth. And this is fantastic information you provided to us.
Thank you.
you.